Hello ladies and gentlemen, and welcome to Distant Learning, and we're into comparing functions, and I believe that this is lesson 6.5, I think is what we're looking at if we're counting everything. So comparing functions, unit 6.5. When you model real-world situation, it is important to select a suitable modeling function. What that means is when you're trying to put a mathematical model on something that's happening, it's important that you choose the right mathematics that will represent that model. If you pick a linear function and it's not linear, then that's not so good. If you pick a quadratic function and it's not quadratic, then that's not so good. And I think that pretty much goes without saying. To make the best choice for a given situation, you must know the characteristics of the function. So in other words, if you're going to figure out whether you should use a linear, a quadratic, or an exponential function, then we need to know a little bit about how those functions, what the characteristics are of those functions. So, tools that can aid you in this decision include graphs, finite differences, ratios, and equations. So, we're going to consider three different functions here. Here's one of them. That's linear. Here's another one. That one's quadratic. And if I can find a blue pen, which I think I found it, that one's exponential. Now, first question, funnily enough, is classify each relation as linear, quadratic, or exponential, and explain how you know that by referring to the equation. Well, when I went through it, I said that that one's linear. And the reason why that's linear is if you remember back to grade 9, y equals mx plus b. You've got this x value. It doesn't have an exponent of 2. It actually has an invisible exponent of 1. And these are numbers, but it's really that x value that's important, that it has an exponent of 1 only. That's how I know it's linear. And then I look at this guy. Well, this, the x squared, tips me off. See how it's not x to the 1. See, there's an invisible 1 there again. Although you don't see it, it's x to the 1. So even though that's just x to the exponent 1, this one is x to the exponent 2. Well, that's quadratic. That's what a quadratic is by definition. And remember, y equals ax squared plus bx plus c. Now, it could have had an x value, but as soon as the x squared was introduced, and the a value here is 1, then that changes that to quadratic. And the last one, y equals 2 to the x. Well, you notice you've got a base number here, b, and the unknown, the variable that's changing, is up here in the exponent. We call this a power function or an exponent. Exponential. Okay? Okay. Complete the table of... I'm sorry, I said we call this a power function. It's not a power function. It is an exponential function. I needed to correct that. I'm sorry. Complete the table of values and sketch all three. All right, so here's the first one again. That's the linear function. And up here we've got the quadratic function. And here we've got the exponential function. And these are my different values of x that I'm going to plug in. Well, when I go through it, negative 3 for x gives me negative 6 plus 1 is negative 5. Negative 2 for x is negative 4 plus 1 is negative 3. Negative 1, 1, 3, 5, and 7. So these are all the y values, or the range values, that are going to come with these x values. So that would be, let's see, negative 3, 1, 2, 3, negative 3, up to 5. Now, before I do a y scale here, I'd like to see what this one's going to look like. Because I may go up by 1s, I may go up by 2s. I need to see here. So if I'm going to take negative 3 and plug it in for x squared, it's going to be negative 3 squared, which is 9, remember. Minus 1 is 8. So this will be negative 2 squared, which is 4, minus 1 is 3. Negative 1 squared is 1 minus 1 is 0. Then it'll be negative 1. Then it'll be 0. Then it'll be 3. And then it'll be 8. And finally, over here, negative 3 up here, well, that's 2 to the negative 3, right? So that's 1 over 2 to the 3, which is 1 over 8, which is a decimal that I can figure out later if I need to. This will be 2 to the negative 2. That'll be 1 over 2 squared. That'll be 1 over 4. 2 to the negative 1 is 1 over 2. 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8. Okay, so now I know what my scale should be. I think I'm pretty safe going 1, 2, 3, 4, 5, 6, 7. So that would be 8 right there. So then this will be 1, 2, 3, negative 1, negative 2, negative 3. We'll do 1, 2, 3, 4, 5, 6, 7. There's 8. Negative 1, negative 2, negative 3. So, negative 3, negative 5, if I'm going to plot this one. Negative 3, negative 3, negative 4, negative 5 is down here somewhere. Negative 2, negative 3 is about here. Negative 1 is here. 0, 1 is here. 1 and 3 is here. 2 and 5 is here. 3 and 7 is here. Let's get a straight edge. Let's connect them. Pretty close to looking something like this. And that is our linear function. That's what a linear function looks like. How about the quadratic? Negative 3 and 8. That's way up here. Negative 2 and negative 3. Nope, sorry, negative 2 and positive 3. Negative 1 and 0. 0, negative 1. 1 and 0. 2 and 3. 3 and 8. So now remember, the curve has got to be kept. You can't just be joining this with straight lines because it's not a line, but it is a curve. So that's a parabola. That's a quadratic. And finally, 2 to the x. Well, negative 3 and 1/8. That's really, well, it's easier to start here as we learned in the other unit. So 0, 1, that's right here. 1 and 2, that's going to go here. 2 and 4, that's here. 3 and 8, that's here. So this is going, whoa, up like that. And then it's going to come into 1/2, 1/4, 1/8, and we're going to have that horizontal asymptote. So we get that curve. Identify the x and y intercepts. Well, okay. The x-intercepts for the linear. The x-intercept is, so an x-intercept is where it crosses the x-axis, and it's crossing the x-axis when y equals 0. So in this case, it's going to be hold on. Let's do this a little bit nicer. So for an x-intercept, you set y equals 0. So 0 equals 2x plus 1. Bring the 1 over to the other side. Divide both sides by 2. Which means that it's crossing here. And that's supposed to be negative 1/2. So that will be negative 1/2 and 0 for an x-intercept. For a y-intercept, you're going to set x equals to 0. So that'll be y equals 2 times 0 plus 1. Y equals 1, so it's 0, 1, which is right here. That's your y intercept. So that's for the linear function. What about for the quadratic function? Y equals x squared minus 1. So for an x-intercept, we're going to set y equals to 0. So take the 1 over to the other side. Square root both sides, plus or minus 1. And we can see that here. The x-intercepts are where it's crossing the x-axis. So it's at plus and minus 1 comma 0, those two of them. And for the y-intercept, well, we can just read it off the graph. We don't have to do any algebra to it. The y-intercept is going to be 0 comma negative 1. So this is the x-intercepts, and this is the y-intercepts. And finally, for the exponential functions, there is no x-intercept because there's a horizontal asymptote, so no x-intercept. But it does have a y-intercept. It's at 0 comma 1 is the y-intercept. Okay, second page. Which of the relations are functions? Okay, we got to go back into what we remember about that. What is a function? A function is any curve that for every x value there is only one y value. And remember, the vertical line test helps us with that. So if I come along here, you'll notice that for every single x value on all three functions, there's only one y value. So they are all functions. All are functions. Each function has only one y value for each x value. They pass the vertical line test. What's the domain and range of each function? Okay, well, looking at the linear function, you'll notice that all the x values could have been used. We only used -3 to 3, but everything could have been used. And all the y values could have been reached. So for the linear function, the domain is x is an element of the real numbers, and the range is y is an element of the real numbers. What about for the parabola, the quadratic? Well, taking a look at this, notice that all the x values could have been used, but there is a lowest y value that we could hit, which is -1. So its domain is x is an element of the real numbers, and its range is y must be greater than or equal to -1, and y is an element of the real numbers. And remember, we used brace brackets, those funny little curly cube brackets that meant it was a set. And finally, what about for the exponential? Looking at this once again, you'll notice that all the x values have a place on that blue curve, but the y values can't ever hit or go below y equals 0, that horizontal axis. So ultimately its domain is the set of all x such that x is an element of the real numbers, and its range is y must be greater than 0, not equal to, it's not allowed to hit that, and y must be an element of the real numbers as well. Identify any maximums or minimum points. Well, for the linear relation, there is no maximum or minimum. It goes on and on and on. So linear, no max or min. For the quadratic, however, it has a vertex. Has a vertex there, and it opens up, so that's a minimum. So it opens up. So minimum value is y equals -1. And what about the exponential? Oh, by the way, the parabola has no maximum. Because it opens up, it keeps going and going and going and going and going, right? And here is the exponential, the blue one. Well, you'll see there's no maximum, that's easy. And there's no minimum. It keeps getting closer and closer and closer to 0, but never touches 0. Now that's kind of hard to understand, but there is no minimum. Whatever value you tell me that is the smallest value, I can get closer. So if you tell me that a half is the smallest I can go, then I can go to 1/4. I can go to 1/8. I can go to 1/16, 1/32, 1/64. And that kind of boggles your mind, but mathematically it makes sense. There's always a little bit of space left over if I'm always approaching 0, but never, ever, ever touching 0. So there is no maximum. There is no minimum. But as x approaches negative infinity, so as x is going this way, okay? So as x is going towards negative infinity, which is off this way, and this is positive infinity off this way. So as x is going to negative infinity, you'll notice that the y value is approaching 0. So it's not a minimum, but you know, it's getting smaller and smaller and smaller. Okay, next page. Calculate the first, second, and ratio of the y values for each function. So, linear. You should know something about this. We did this in grade 9. The first differences should all be the same if it's going to be linear. So let's remember what the y values were. I'm going to go back. These are all the y values. So I'm just going to transpose all these values over, okay? So this is going to be -5, -3, -1, 1, 3, 5, and 7. I'll do the same for the quadratic. So it's 8, 3, 0, minus 1, 3, 8, 3, 0, minus 1, 0, 3, 8. And for the exponential, it should be 1/8, 1/4, 1/2, 0, no, not 0, silly me, 1, 2, 4, and 8. Okay, so let's find the first differences. The first difference here will be -3 subtract -5, which is negative is positive, so -3 plus 5 is 2. This one will be -1, -3. Negative is positive, -1 is 2. 1 subtract -1, 2. 3 subtract 1, 2. 5 subtract 3, 2. And 7 subtract 5, 2. So all the first differences are the same. That is characteristics of a linear function. Hence that rate triangle that we talked so much about in grade 9 and 10. Quadratic. First differences. 3 minus 8. -5. 0 minus 3. -3. Minus 1 minus 0. -1. 0 -1. 1. 3 minus 0. 3. 8 minus 3. 5. So these are not the same. So it's not linear. Second finite differences. Well, we just do the same thing, guys. You just take these two, -3, subtract -5. Negative and negative is positive, so that's going to be 2. -1 subtract -3. Negative is positive, so it's 2. 1 -1 is 2. 3 minus 1 is 2. 5 minus 3 is 2. These are all the same. So if the first finite differences are not the same, it's not linear. But then if the second finite differences are all the same, then that is quadratic. Okay, last one. 1/4 subtract 1/8. Now I'm going to use my calculator for this. So 1/4 is 0.25, subtract 0.125. And that gives me an answer of 0.125. 1/2 subtract 1/4 is 0.5 subtract 0.25. So it's 0.25. 1 subtract 1/2 is 0.5. 2 subtract 1 is 1. 4 subtract 2 is 2. And 8 subtract 4 is 4. So these are not the same. Hence, not linear. Second finite differences. So we do it again. So 0.25 subtract 1.25. I think I said that wrong. 0.25 subtract 0.125. And that is 0.125 again. 0.5 subtract 0.25 is 0.25 again. 1 subtract 0.5 is 0.5. 2 subtract 1 is 1, and 4 subtract 2 is 2. These are not the same. Now, it would make sense to try to do the third differences, but that's not what we do. Once we know that the first finite differences are not the same, once we know that the second finite differences are not the same, we stop doing finite differences. And what we look for is a ratio of the y values. So we want to know the ratio of this one divided by that one. So in other words, you want the ratio of 1/4 divided by 1/8. Now that's pretty tough to do. So what I'm going to do is I'm going to use the decimals again. So a quarter, remember, is 0.25 divided by an eighth, which is 0.125. And I get an answer of 2. So this ratio is 2. Then I do the ratio of 1/2 over 1/4. So 1/2 divided by 1/4. And again, that's hard to do as fractions. So change them to decimals. 0.5 over 0.25, which again is 2. So now we're going to do the ratio of 1 over 1/2. 1 divided by 1/2. Well, again, that's hard to do, so it's 1 over 0.5, and using your calculator, you'll get 2. And then 2 divided by 1, which is 2. And then 4 divided by 2, which is 2. Notice that the ratio of the y values are all the same. But it's a ratio. It was that division. That means that it's going to be exponential. So once again, you got to go through the first finite differences, the second finite differences to make sure it's not linear, make sure it's not quadratic, and then you check the ratio, and then you're looking at an exponential function. Okay guys, that's it for this one. We'll talk to you soon.